Okay, we can kick off the week now. So we're looking at comparing a couple samples to something that we'll do on Wednesday is looking back at paired samples. But in this case, we're doing two independent samples, and we have looked at two sample T procedures when the variances are equal. We're talking about pooling that, but of course in some data we'll look at it and it'll be clear that the variances are not really equal, so that pooling assumption seems to be not accurate. And so there's a way we can do the two sample T procedure with unequal variances. And so we want to see about doing that. There's a little wrinkle once we relax that assumption, and it changes the test statistic and how we evaluate it just a little bit. But there's a couple ways that we can deal with this departure from the assumption slightly differently. Instead of dealing with data as it is with the unequal variances, if we change it to ranks, might be one way to address that. That's also useful if there's outliers, right? So our data are not quite normal, but have a few more extra large or extra small points, so they're outlying. And there's also this idea of a permutation test. It's a way to generally look at distributions and how they compare, right? And so we'll look at these different procedures. There's this and more that people have developed, different variations. And in this, we'll try to keep track of what are the assumptions, what exactly is being tested, how does it evaluate the test statistic, and does it seem to make much difference? Right? So it's possible in looking through these things to think, oh, it's just a whole series of procedures. And we'll also talk about kind of the goal, the overall perspective. What would you do in practice, I think, in looking at comparing some distributions? Would you use more than one of these things? Would you use them together? What would you do? Because ultimately we want to learn from our data. And if we can employ different procedures, different tests, different models and assumptions, and get a little keener insight into what's going on, then we can learn something, right? But any questions? Homework 2 is due on Wednesday. I'll have office hours today and tomorrow. So if you have questions about that, please don't hesitate to come by or write, right? So with a two sample T test, two samples, these are independent samples, not paired for each other. Right? We have group 1 and group 2. N1 individuals in group 1, N2 in group 2. And for testing hypotheses, are the means equal to each other? Versus an alternative that they're not equal to each other. Or it could be one-sided depending on the context. We would calculate generally the averages, y bar 1, y bar 2, and the two sample standard deviations for the data. And if we think that sigma 1 and sigma 2 equal variances, if that's our assumption, if that seems reasonable, now they won't. S1 and S2 will never be exactly the same, but if they're within 50% of each other, if one's double the other one but not quite, you can basically proceed as if they're equal, and it won't affect the quality of the procedure that much. But if one's 4 times as big as the other one, or 5 times as big, it starts to get a little bit implausible, and it will ultimately impact the procedure, right, in terms of error rates and things like that. But if it is equal, we calculate a pooled version. We take a weighted average of the two variances, N1 minus 1 times the first sample variance, N2 minus 1 times the second sample variance, and divide by the sum of the two multipliers, and that becomes our pooled versions of things. And our t-test statistic then is y bar 1 minus y bar 2, the difference of the means, and then standardized by the standard error, which is the S sub p, and divided by n minus 1 for the first group and n2 for the second group, right, and square root. Right? And that's our test statistic, and we compare that to a t distribution with n minus 1 plus n minus 2, n1 plus n2 minus 2, right? The sum of the two individual degrees of freedom. Right? And if the null hypothesis is true, and the variances are really equal, this should, and the data are roughly normal, right? This should give us significance levels. If we say it's a 5% significance level, we should reject the null hypothesis about 5% of the time, that it should be quite accurate in terms of its performance when the null hypothesis is true, right? However, if this is not equal, then it doesn't make any sense to pool them, because you would take one small variance and one large variance and average them together and get something in between, and it's not really accurate for either group. Right? So this is sometimes called, there's different people that have studied this and give procedures associated with this. Welch is one, Satterthwaite is another one that you will see. So there's a couple other names, and I think this is how you spell Satterthwaite. I always forget where the H is. So. This one uses a different t statistic. A little w here for Welch, and it's y bar 1 minus y bar 2. And so the variance of this thing is sigma 1 squared over n, so we're just going to estimate that by its sample variance. And they're independent, so then the variance of this difference is the sum of the two variances. And so we're going to put this one in here, and then take the square root of that whole thing. So that will be the t statistic. And then the wrinkle is that under normal probability models, this thing doesn't actually have exactly the t distribution. The distribution theory doesn't quite work out, because really here you have a mean. If the means are the same, you have two different variances, and the probability theory just doesn't work out to closed form. This is actually a famous problem in the simple case. The fact that you don't exactly get a t is something called Behrens-Fisher problems. And people in probability theory have worked on trying to approximate this distribution and figure out what it would be under certain restrictions on the, so anyway, there's this kind of abstract probability theory that gets done. For us, the practical point is, this is what degrees of freedom to use there to come close to an approximation, right? It's really kind of a mixture, because you have two different variances, and so it's kind of a funky thing. That it has a mean, it has to have a variance, right? But what shape is it exactly? And so the idea is then to choose the degrees of freedom so that you match it. The mean is, the mean is going to be 0 because the mean up here is 0. But then there's a variance, and then the question is, what degrees of freedom makes that t the appropriate width to end up matching the distribution. This is exactly the distribution if the data is normal, and so there's no question about that one. But different people have come up with different approximations and ways of getting at it. This degrees of freedom here. So degrees of freedom is, for this Welch t-test, is the standard error to the fourth over the standard error of y bar 2 to the fourth over n2 minus 1 plus the standard error y bar 1 to the fourth over n1 minus 1. And these different components in here, the standard error for y bar 1 is S sub 1 over the square root of n1. S2 over the square root of n2. And then the standard error, this one, SAW, is the S1 squared over n1 plus S2 squared over n2, and the square root of all that. So this thing usually comes out, is usually larger than the minimum of the smaller individual degrees of freedom. And it's going to be between that, and it's usually not as much as n1 plus n2 minus 2. So it's somewhere in between. Like you lose a little bit of spread because one of the variances is extra small, right? In between there. And so, yep, that would be the calculation. We'd get our samples. We would have already calculated S1 and S2. Instead of doing the pooled version, the complication comes in this degrees of freedom. This is implemented in R or other statistical packages, so rarely would we have to do this by ourselves, but it would give us a different degree of freedom, right? That adjusts. The degrees of freedom, this number can be a decimal in there, that's okay. T distributions, the numerical approximations can use decimals in there, so it will come out to be a decimal. If the variances are pretty close to equal, I believe it comes out pretty close to this one. But if they're really different, like one's really small and one's gigantic, then it's pushed down to a smaller value. So get something in between. And the purpose of doing this is that if the variances really are unequal, the initial assumption, right, that's used in the equal variance case gives us error rates that aren't near 5%. They're more. It makes mistakes more often under the null. But this one, because it's adjusting the degrees of freedom and accounting for the actual variance, right, gets closer to 5%. So that's one procedure, right, for doing this. Right? But a different way, right, of looking at this, right, we'll do something called a permutation test. So say we still have the same hypotheses. The means are the same versus an alternative that they're different. And our test statistic, we're going to take the sample difference in sample averages. And now our goal is to evaluate that our observed statistic value is at extreme. Right? And so a different idea, instead of going to T distributions and statistical theory, right, is to consider this null hypothesis a little more strictly. Right? So that just says the means are the same. What if the two distributions, right, the two distributions for the distributions for the two groups, the two populations or two groups, are exactly the same? One way to consider, to think about this, that puts it in the best context, I think, is like a randomized controlled experiment. Somebody comes in and you randomize one group to treatment, another person to control, so there's a little coin. And you then see an observed difference that maybe is higher in the treatment and lower in the control, so you get a positive difference. Well, what if the outcomes really would be no different at all, and the thing that if you got a positive value of the statistic, it's just purely due to chance, right? So if that's true, if there really was no difference in the distribution at all, you could have just by chance taken your two N1 plus N2 values and randomly mixed them all up and called the first N1 the first group and the next N2 the next group. Right? You could have just randomly mixed them all up and arbitrarily labeled some treatment and control, and that could have been equally likely to be an outcome that you would get. Right? So to study this distribution, right, we're going to put the N1 plus N2 values that we have into a bucket. Right. Randomly pick N1 of them, and based on those N1, compute a new value of y bar for the first group. The other N2 of them are in the second group, and we're going to calculate y bar 2. So we're keeping the N1, N2 sample sizes the same for the first and second groups. And then our simulated difference, our T star, is y bar 1 star minus y bar 2 star. That would be one random reorganization of the data, which would be totally plausible if in fact there really was no difference at all. No change in variances, no differences in other parts of the distribution. And do this, some large number of times. So if you do that, 1,000 times, 10,000 times, you have 10,000 things that would look like other samples under this very sharp null hypothesis. There's no difference. And one way we could evaluate that difference then is to look at the differences in means. Right? And so we could calculate the probability that our observed statistic, that our T star is greater than or equal to our T statistic by the number of times, the number of T star that are greater than or equal to our value of T over the number of simulations that we do. So if in only 5% or less of the times our T star value, 1% of the time or a very small percentage of the time, we actually can get something as big, if it's really mixed up, that would suggest that the difference we actually saw was in fact extreme, right? And not consistent with just the null hypothesis that there's really no difference, right? So instead of using the T theory and dealing with the Welch's degrees of freedom, this type of simulation, permutation of things gives another evaluation. The thing about this one is you're not really stuck with means, right? Because once you do this permutation, right, anything you want to compute to summarize that distribution, right, could be calculated, right? And then you do that 10,000 times. So any statistic you think would be useful, medians, the first quartile, right? The minimum value in the samples, the standard deviations themselves, or the log of the standard deviations, whatever you want. Right? So this idea of this permutation and looking at the distribution of some statistic under the sharp null hypothesis allows you to evaluate many different things, right? And maybe the means are not ideal for seeing some difference. But anyway, permutations could be done with means too. And there's no real assumption, that variances are equal. The hypothesis it's really testing kind of, might reject that they're equal, maybe because the variances are different, So there could be some kind of more, the null hypothesis is a little bit sharper, right? The other one said before just if the means are equal or not. And the t-test really is focusing on that. This one does a little bit more. So it's a little more complicated, right? right? But it doesn't stop there, right? A third one to give one before looking at some code. I'm trying to break it up to some presentation and then go to like some data, right, like that, is what's called Wilcoxon or Mann-Whitney, two other people, rank sum test. So in some of these tests, this one's called it's kind of in the realm of things called non-parametric tests. They're tests that don't assume the data is normal or don't assume that the data is exactly in a parametric statistical form, that it doesn't come from some distribution, right? And some of these tests were developed by different people in different fields, psychology or biology or some other, or within statistics and math itself. So some of these things have multiple names. And there's, you look on the internet for different definitions of this, and they will give slightly different presentations. So the software that's out there might do slightly different things, but they're all going to be kind of a similar flavor for doing this, right? So we have the data y1i and y2i, and there's, for the first group, there's N1 measurements, and for the second group, there are N2 measurements, and these are the individual data values. Right? And the data might be skewed. Right? It might not have a normal thing. It might have outliers one way or the other. It might have gaps. It might have funny patterns. And you just don't know what distribution it is. Right? And so put all N1 plus N2 data values right together. So we have N plus N2, and so let's just call them y sub I for all the data values. Right? I'll put yj, j going from 1 to N1 plus N2, so that's all of them. Right? Instead of dealing with the data values themselves, we're going to compute ranks. We're going to put them in order, in ascending order, and give them ranks 1, 2, 3, up to y sub j. Transformed into ranks. And the ranks, these go 1, 2, 3, right, up to N1 plus N2. Right? And the aspect of ranks is that no matter what the distribution was, if you have N1 plus N2 data values, you always have the same ranks, 1, 2, 3, up to N plus 1, right? There's no outliers. In some cases, there might be ties, and that is part of the discussion that you'll see if you look online or other textbooks about how to evaluate these things with ranks, but that's just kind of a side point. Right, and so the statistic that gets used, right, is we're going to sum up these ranks and the j, the index that we're going to add up is the rank j from the smallest group. So say N1 is smaller, that N1 is less than, suppose N1 is less than N2, or less than or equal to N2. They could be the same size, right? And we're going to look up the ranks when the data are all combined together from the smallest group. In this case, I'm saying it's group 1, just as an illustration, right? So that's a statistic, right? And we could look at this statistic in a couple ways. One is just a pure randomization, right? If it was totally, if there's really no distribution, difference between these distributions, either in terms of the mean or anything else, right? You could randomly pick n1 ranks from the total set and pretend those are the ranks for the first group. And if there was really no difference, that would just be a random realization, of data, right? So you could again randomly pick them and add them up. So you could go through randomly picking n1 ranks out of n. So how do you evaluate t? Is the observed value of t extreme under a null hypothesis of no difference between the groups? So we want to evaluate that. So one option is we randomly sample n1 values without replacement. We don't do any repeats. From 1 to less 2. And then we calculate the sum of those sampled ranks. The n1 values would be called these RJ stars, right? And we add that up. And we do that sampling, a large number of times. So we get 1,000 values of this sum of rank statistic. And then we can see, is ours that we had particularly high or particularly low, right? If the data that we actually have are on the low side, its ranks, when combined with all the other data, is going to be kind of small, right? And so we get a small value of t in practice, and then our random simulation is going to be bigger, right? If, however, our actual sample has kind of big values out there, and we randomly sample ranks, then ours is going to be larger than a lot of the cases. And so, yeah, you can get a p-value. The other thing, the other way that this is done is the normal approximation. To the distribution of t. Right, so under the null hypothesis, t is a random sample of numbers 1 through n1 plus n2. Is that kind of a practical problem, right? We should be able to figure out what would be the average value of t, right? The expected value of t, the average value, it would be the figure out what the average rank would be from randomly picking from this. There's n1, the average, kind of at the average of these numbers, n1 plus n2, plus 1 gets put in there over 2. Randomly sampling ranks, the average rank is this, right? And you're going to pick n1 for the smallest group, so that's the average that you would have from taking random samples. And you can also get the standard deviation. The standard deviation of t. I have the standard deviation of all the ranks. So if you calculate the standard deviation of 1 through n1 plus n2, n1, and so there's different ways that this formula gets expressed, right? So you can calculate the standard deviation of that. And the t is approximately normally distributed with that mean, right? And that standard deviation. So this is not saying that the data themselves are normal in any way, right? but it's saying that the sampling distribution of that statistic, as long as you have N1 being large enough, so N2 is also kind of large, is approximately normal. Right? Which means if you needed to judge, is our value of t unusual, you could compare it to this normal distribution, right? There's a nice bell-shaped curve, and if the null hypothesis is true, we'd expect to be kind of in the middle of that. But if our actual statistic is extreme, right, then you'd be able to judge. So there's kind of a couple ways that gets done. I mean, in the R software, doing this enough times or doing the actual combinations for nearly all or for a sample of 10,000 is called more the exact method, and then this is more of an approximation to that p-value. If the p-value is less than 0.01, both things are kind of going to give you the same thing. If the p-value is, say, something like 0.2 and not small at all, both of these things will kind of give the same. If you only have 4 or 5, 10 observations in one group and 15 in the other, doing them all, not even simulating, is possible, right? And so you don't need this approximation. Once it gets bigger, so this normal approximation also is motivated by not pre-computer days, but older computer days, right? Instead of evaluating something 10,000 times, particularly if you had to shuffle cards or some funny thing like that, right? Or a computer would take a minute for each small evaluation, you're only going to do so many, right? But if the computer can do it 10,000 times in 5 seconds, why not? But this theory was, you do a few calculations and then get a tail area, right? So the big picture is we want to compare distributions, and a very standard thing to do is do a 2-sample t-test with equal variances. But if the distribution doesn't really match that, the assumptions aren't very accurate, and our procedures won't be so good. Right? So let's look at some examples. Any questions about? So we're going to look at the second case study. There is one example in chapter 4, and this one had to do with educational research. Right? There were 28 ninth graders in Australia, and they're going to receive training in coordinate geometry in one of the 2 waves. One of my daughters is now taking geometry, so it's kind of interesting. And then after the training, the students were asked, so I'm wondering, 28 ninth grade students, are these 14 in one class, 14 in the other class, or class sizes here now are about 28 per class, so could they divide a class into two groups and teach them differently? I don't know, because kids talk to each other, so it's not. I wonder about if that'd be independent groups. But after the training, the students were asked to solve a coordinate geometry problem, and the time was recorded. And 5 students in the conventional did not complete the solution in the time. So does one teaching method lead to a faster or more correct solutions, right, for this? You do this thing, I attach it. The names of the data set that are on there are the time, the treatment, and the censored, right, whether they didn't finish in the time allotted, right? And that complicates analyses. There's 5 that are censored. The 5 that were censored were given a time of 300, right? It's kind of conservative in some way that, it's not clear that they could have done the problem. But if would they have gone on for 10 minutes, or would it be some big value? So anyway, that's kind of a data truncation, something that they've done here. So that could affect the analysis, right? So a lot of biomedical analyses looking at survival time, or engineering analyses looking at how long does it have before something fails, and so on. And so those are the data. The censoring. There's 2-way table, censored, yes or no, and treatment, conventional modified. In the modified treatment, there's 14 non-censored and 1. So the 5 are in the conventional, and that's what the paragraph said that on the help file for that. if you, on your data set, on your computers, install the library for Sleuth 3 and then type library and then this data, you'll get the help file. I still need to fix how this works here so that I don't have to do it each time. But anyway, I still have the data for us, and here's the plot. Let me try that again. It looks like the conventional, right, is much higher, right, than the treatment group, right, in there. And so let's see. I'm not going to put it in. Here's the plot for the conventional. Here's the plot for the modified. And so looking back between these two things, the conventional kind of starts here at about 100 seconds and goes up to 300, whereas the modified one is lower. The standard deviation similar. Standard deviations are not too different. I wouldn't probably worry about it too much with this example in the book, which is kind of interesting why they put this one there. But anyway, we'll use this one. In one way to say that something is going to be a function of something else in R, this little tilde thing, right? So time as a function of treatment, and so it's going to divide time by these two groups. Right? There's an equal number of observations. So you want to, I don't know, you want to either make sure you're not doing a paired or tell it that it's not paired. And one argument is to say that the variances are equal versus unequal. Right? Does it make a difference? Right? So if it's equal, we get this thing, two sample t-test. The t-value is 4.09. Degrees of freedom are 26. That's the number of rows of case study. Right, it's 28. It was N1 plus N2 minus 2, so it's down to 26. Right, as the degrees of freedom. See that there? And it gives us p-value of 0.0004. Highly significant because it's so small. There's clearly a difference, an average between these groups. Right? And it gives the two means and gives the two confidence intervals. And it gives a confidence interval for the difference. It's still pretty wide in terms of the time, but there's only 14 in each group. So and there's a lot of variability in how fast the students solved that one problem. Right? If you make it unequal, so that it's false here, it gives you, right? It does this Welch procedure, Welch two-sample test. It gives a degrees of freedom that's 24.83 right, instead of the 26. So it's reduced a little bit. It's not reduced a whole lot. The variances weren't so greatly different, right? So it's not going to give you that penalty by reducing the degrees of freedom so much. The observed difference is still the same. The means are still the same as before. Now this is the p-value. It's not much changed. It's a little bit smaller, I think. A little bit bigger, rather. Before it was 0.36. There's a 3699, and this one 3976. So it's not quite as small. Right? But that reflects we have a smaller degree of freedom. So the t distribution is naturally wider. And also, instead of that pooling of the variances, the combination of the two is going to be a little bit bigger. So it doesn't make too much difference in this. And the confidence interval is not much changed, right? And so in this case, either way you do it, you get the same result. If you checked both ways, I'd probably report the one that's equal because the variances are kind of equal. And to me, if you're going to say something about the means, it kind of makes sense that the other things in the distribution are the same. If things suddenly are different in other ways, then there's a little bit more than just the averages. So anyway, the one where the averages of the variances are equal is the one I would like typically. Right? But this is the way there's the Wilcox test, this Wilcox and rank sum test, is built into R. Right? There's a Wilcox test. Time is a function of treatment. And it has a few options. You don't necessarily have to give all those options in there. You can do help of these different commands. So rank sum and signed rank test, the 1 and 2 sample. The 2 sample is also known as Mann-Whitney. So we have X and Y, and then it has some different options that can be there. The data values, this is another way to specify the data, right? We don't need mu, it's just going to be a difference of 0. Paired, is it paired data? We're not paired. The default, I think, is that it's not paired, right? So computing an exact p-value, whether they enumerate all possible cases, which is okay as long as we don't get a really large data set. It will just take a while to do it. If they do the normal approximation, you're dealing with integers for the sum of the ranks, and so there's a continuity correction that's there. And so anyway, some of these things can be used, or right, if you do this, you can also report a confidence interval for the average difference, and in this case, it does the Wilcoxon rank sum test with the continuity correction. It's exact equals false, so it's using the normal approximation. It gets a statistic here, this W. Right? And I don't use this all the time, and so I don't, off my top of my head, this is in the context of the ranks, so the W's can get really big if you have larger samples, so that statistics by itself doesn't have that much meaning. It doesn't have an intrinsic meaning for me, right? But the p-value is, it's not as small. It's small. There's no question that there's a difference between the groups, and the modified version is teaching that one aspect of geometry better or faster. Right. And there's some difference in ranks, that the average ranks between the two groups seem to be, well, I don't know, that means the sum of the ranks between the two groups. So there were 28, so if you add up all those numbers, there's that difference. Again, that's in the context of things. Right. But the p-value really is testing, are they the same? And no, that one is quite a bit bigger than the other one. Right? And if you run it with exact equals true, it gives you the p-value is about the same number. Yeah, it really comes out to be the same number there. But it doesn't give you a confidence interval because there are a few ties. There are a couple of the values that are repeated. 300 is repeated, 80 is also repeated. So the mechanism of it, of evaluating things, it seems like to me it seems like they should rewrite the software to deal with that in some principled ways rather than give it an error message. But anyway, in the non-parametric literature, people have thought about that. So anyway, that's that example. It doesn't seem to make much difference, but it's certainly possible. For a permutation test, right, we would want to choose 14 of the 28 and consider them in group 1, right? And if they're the equal means, then any of those, well, really for equal distributions, then any of the ones that are taking the conventional or modified could be put in the first classroom, assuming these suits are splitting classrooms, right? And that would be called the first classroom, and it's just arbitrary. And if things were closer, then we might wonder and think, well, maybe it's just by chance that one group is a little higher than the other, right? They had a little better day, whatever. We're not going to look at all possibilities. There's about 40 million some ways to reorganize. Choose 14 out of 28, but we're going to simulate 10,000. That's going to be enough. And again, with the permutations, we can look at, we're not restricted to looking at means. You can look at other things that are there. So we're going to set that up, set up those two places to hold. Then we're going to sample 14 numbers out of the 28 and compute the differences in means or difference in medians, like that. And I'm going to keep track of I'm going to ask what percent is, so the permutations for the means, how many of our simulations are greater than or equal to the actual difference that we got. And I'm using that little which, just a little indicator, which is control, conventional, and modified. I find that convenient to create a little index so I can keep track of which ones are there. And that's, so that's 0.0002, right? There, and the median one is basically 0, right? The medians are never that extremely different in my 10,000 samples in this case. So again, the permutation is going to give the same result. Requires a little more programming to do that little loop in there. I'm going to take that out of memory, so I'm not using that one again. But anyway, so that's one example. Now this example in the book, I wonder, it doesn't seem terribly well motivated, right? Because there wasn't a really big difference in standard deviations. I wouldn't think that methods between equal or unequal would give that much difference. They weren't really outliers. So the permutation, I wouldn't think would give that much different than that, right? In the help file, which I had up there, right? Some of these help files down at the end, besides the things that come out of it, different notes, some academic references, related commands, right? Sometimes are some different examples, right? And so this Hollander and Wolf is a book on non-parametric statistics that goes through a huge number of data structures and talks about how you would compare different aspects of distributions without making a lot of assumptions about distributions, right? So it's not a bad reference, kind of a classic text. And they have one example, Hamilton depression scale factor measurements in 9 patients with mixed anxiety and depression, taken at the first and second visit after initiation of a therapy administration, right? Oh, that one is paired. Which one did I do? That's a paired test. Oh, here, I did this 2 sample test. So, sorry about that. That's not the one we're doing. But permeability constants of the human chorioamnion fluid, right? Not fluid, membrane, at term and between 12 and 26 weeks of gestational age, right? So at term, 37 weeks, so earlier versus later. And is it changing? Right? So it's kind of interesting to think about how would you get those measurements, that kind of an invasive procedure. Maybe they can get it from X-rays or sonograms or something. I'm not sure. But anyway, it has the values there and the test. So this illustrates the procedure. So here's X and Y. The standard deviation of X is that. The standard deviation of Y is smaller. So in this case, the standard deviation of Y is half that of X. So that's more where I thinking about worrying about the equal variance assumption. It's also kind of small sample sizes. So if X or Y is not very normally distributed, then you kind of worry about that. Is 1 greater? So if this is supposed to be something that is growing, X and Y, p-value, it's not significant. They have it there, right? And this one, this is this one, right? And also p-value is not significant. These couple of different ways of doing it. Why would you use that here? In addition to the shift in median, right, kind of in center, there is this bigger spread. So you might be interested in doing that. If you do a t-test for the difference in means, the equal variance one, give a p-value of 0.13, right? Not significant. That's consistent with the other ones. Unequal variances, degrees of freedom went down a little bit, not too much. The p-value happened to shift a little bit closer to 0.05, but still didn't cross over that barrier. But it's still consistent. There does not appear to be a significant difference. Now, does it look like there's going to be a significant difference? I mean, it kind of looks like the medians are different. It looks like there would be something, right? So this one, you kind of wonder, our sample size is just too small, right? There is a lot of variability. This is different women have this membrane, different thicknesses. There is variability. If this is something that's supposed to be growing and thickening as the baby gets bigger, if that's part of what it does, or maybe getting thinner near birth, right? So it's changing in some way. You might think that it would be different at two different time periods. But there's such a small sample size that it doesn't come out as significant. All the tests are consistent that way, so that's good. In these two examples, different procedures give consistent results. And so that is good, that is supported. The fact that it had small sample sizes or that there are different standard deviations, any article that's describing the outcome for those women is probably going to give that. If you only gave the equal variance t-test with a small sample size and unequal variances, some people will say, why are you doing that? Or a journal reviewer on that article will come back and say, well, maybe you should check some other procedures. Right? If you thought about that beforehand and said, we checked other ways of looking at this, and it's still not significant, right? Or there's no difference. Everything's consistent, looked at different ways, that's great. And so this one between you, different procedures, that so this strengthens the overall conclusion one way or the other, and avoids criticism from relying on statistical assumptions or not noticing something. You want to show people that you've noticed things about your data and have taken that into account. If the results had been inconsistent, then there is a need to explain more. So, looking at multiple tests, you don't necessarily have to go overboard with things and look at, go search out all the different possible ways of doing something. But if something raises a red flag and says that maybe something isn't going to be quite right with this procedure, and you check the most common alternatives, such as these, and you do get inconsistent results, like it's not significant with one and significant with the other, and it's kind of interesting, right? It kind of needs to say a little bit more. It gives you a tool to try and explain and maybe say, well, maybe there's a difference, maybe there's not. It looks like if we had done something different with those 300 that were censored, right? If we made them 400 or 450 or somehow took them out of the data set, right? That then we're talking about the students who didn't get the correct answer, right? or something like that, right? It becomes a little more complicated. There's more to explain, and you're trying to generate scientific knowledge, right? So if you do different tests and they tell you different things and you have to dig into explaining what's going on a little bit more, Is it variability? Are there outliers? Or is it just simple that you had such a poor sample size that you didn't get that, right? So, yeah. So, one other thing to think about these examples. In these two examples, this one. Would you use two independent samples? Both of these were presented as two independent samples, one by our textbook and one by the health file in R, which is coming from a different textbook. How about the second example? Yes?
I feel like you could do a paired one sampling the women between, what was it, 12 and...
10 to 12, yeah, like
Yes.
10 to 26
Yeah.
weeks, and then at 37.
Yeah.
Yeah,
You sampled
right.
them twice during their pregnancy and changes.
Yeah, right. So that, to me, would make a lot of sense, right? That so the membrane. Now this R example. I think it was 10 to 26 weeks, and then at 37 plus weeks. You could have, differences. Right? You could have matched pairs. Right? So that if one woman, because of her size or genetics or environmental influences or diet or something, had a thicker membrane at this time and a similar thicker membrane at this time, then the difference might be quite small, right? Or if there's actually a growth, or whatever, that there's these things that would influence things here and here, and then the question is it really different? And because you're taking a sample of women at two different times, why not have that matched pairs, right? But if you did have insurance records or something where you had a massive number of individuals with that information in electronic health records and a similarly massive amount of information here, and you wouldn't necessarily pair them, right, you might take that difference. But if you're doing a separate study where you're seeing the women at multiple times, then pairing it makes a lot of sense. Education one. A little harder to think about pairing, but if you had a pre-test and could rank students by pre-test and kind of split students in two groups, not by high and low, but just kind of randomly, maybe take the two with the lowest pre-test score and put one in each group, and two with the next level of pre-test score and put them in the groups, so that you could create some pairings, right? So by doing that, you could also learn, do the students who start out with a high scores, do they both benefit from the modified method? Does it help students with the lower? Right? So by having that pretest score one way or the other, you could look at a little more subtle change, right? Just not time on that exam, but time compared to where they started from, because not all the students started the same. So in this one, you say you could create pairs with some effort. At least you could take a baseline measurement, baseline or pretest measurement, into account in some way. Maybe even just their grade in algebra, right, before taking geometry. Something like that. And, you know, for me in this example, a bigger question is, are students really independent? It's the second week, just starting the third week of school, also for this, for the public schools here. My daughter's in a geometry class, and some of her friends are in a geometry class with a different teacher. And they're already talking about, what are you doing in your class? So, even if these 28 were split into two classes, you know, they're still gonna, and so, how doing an experiment in education in a setting like that's pretty tough. This final example is some data in R. So data, you type R, there's a bunch of different data sets that are there. That's kind of the base for getting some data sets for the student. Kevin Connor was the one assigned for Wednesday to present something on transforming some of these data. And it's there. One of the data sets is this air quality. So just typing that. And there's a help file. We'll talk about that data set with some structure and things like that. I'm going to attach it. There's different months. These are the ozone over time. This is the box plots of ozone by month. So June, and then if you wanted to compare number 5 to number 8, say, and pretended they were independent measurements, you know, then this one has, well, there's a big outlier, there's different variants, you know, and you run the examples. It's very possible you would get different results, whether you considered it equal variance or not, whether you did a t-test versus the permutation or Wilcoxon, and anyway, so it's kind of another data example where things might make more of a difference if you did things in there. So when we, on Wednesday, we'll look a little bit more about transforming data. Sometimes data are really skewed and you want to take logs or something, and Connor will lead off with our presentations like everybody will do, to look at a few interesting examples to feed into that. And I'll return homework 1 on Wednesday too. I think you're going to do something over the weekend. I don't quite good at that. Yeah. Question on. So, if this is looking at one-sided, how many of these simulated means are greater than the actual one? So that's one-sided. But a two-sided hypothesis, we care about both tails. So the p-value gets multiplied by 2. So this is, yeah, if it's just doing, is the mean greater than or equal to that? Right. This is our observed difference. Right. So that would just be one side. And then the two-sided alternative would get multiplied by 2. This is a parameter thing for, this is just making it one plot per graph. I think maybe on the other side, back here, I wanted to put the 2 histograms side by side. Now it doesn't work so well on this little screen here, but on my when I'm doing it on my my computer in my office, then I can put these 2 histograms side by side. And so it's matrix format row, so 1 row, 2 columns. So this will change the plotting so I get 2 side by side. That was the purpose of doing it there, to get the 2 histograms beside each other. And then this one, I just wanted to see the box plot. I didn't want to see it small, I wanted to see it big. So putting it 1 by 1 is just the default one graph. So, yeah? Yes? Uh-huh. I have it, you know, kind of now after class or before my class. You know, like at 1:30, something like that?